Hello, chemistry students. This is Professor Sean McMahon with another lecture. Today, I'm going to be discussing Chapter 6, Compounds and Their Bonds. And primarily, we're leaning into this because we covered in Chapter 3, matter. And under matter, we categorize that with pure substances and mixtures. And then in Chapter 4, we focused with primarily pure substances, but under pure substances, there were the elements and the compounds. And in Chapter 4, we focused on element and atomic structure. That's why we had to discuss the nucleus, the electrons, the electron arrangement, how it gives it the physical and chemical properties for each element. The singular of an element is an atom. That's why we talked about atomic structure. Chapter 5 would have actually led us to go into what's called nuclear chemistry, where we would focus on the nucleus and its decay and the different types of decay reactions. I typically move Chapter 5 to the end of the semester. That's geared more towards people going into the allied health field. This Chapter 6 is actually a good for just introductory chemistry, general chemistry. If we're going from Chapter 4, atomic structure and elements, now going to Chapter 6, now we're going to talk about the other types of pure substances that we learned of matter, compounds, and the bonds that are found in compounds. So I hope you enjoy this. Here we go. So let's look at a compound. So here we have sugar, table sugar, C12H22O11. So we know it's composed of the C, that elemental symbol is carbon. And carbon in nature and as an element is found, well, there's actually two allotropes. There's graphite, you can think of it almost as coal, and then under extreme conditions and heat and pressure, you form a diamond. Okay, so those are the two allotropes, those are the two solid forms for carbon. Now, oxygen's different. It's found in nature as a gas, and it's an O2 because it's one of those 7 diatomics that I told you about, and we'll be discussing those as well. And then you have hydrogen, the simplest of all elements with just one proton in the nucleus and one electron orbiting that nucleus. So the properties of sugar are completely different from all of these properties of the individual elements. So that's kind of what I want to emphasize is compounds, no matter what they're made of, are going to have different properties than the individual elements that make them. So here's another example. We have sodium. Sodium is a highly reactive metal. It oxidizes quickly. If you throw it in water, it actually kind of explode and produce a great amount of energy and heat, producing a basic solution. You could take chlorine, another element that's a diatomic, meaning 2 of them combined, which is a yellow, greenish, noxious gas that will kill you. And when you put them together, you make table salt, sodium chloride, what we throw on our French fries. So I always think that's really interesting how the individual elements have these really kind of cautionary properties, but yet combined, we use them as a seasoning. So the properties change completely. And when these react, because essentially this is a reaction, we can actually show the reaction using chemical formulas. So that's kind of what this chapter is going to introduce, because in Chapter 7, we'll discuss the different types of reactions. In Chapter 6, we're going to talk about how can we determine the formulas. So again, sodium, right? It's an element, it's a metal, and it's singular unit as an atom. So we just write Na for the elemental symbol, and the subscript S stands for at room temperature. It's a solid. Typically, your metals are going to be solids with the exception of mercury, which is a liquid. Chlorine, which is an element, but it's one of the diatomics, is found as a gas at room temperature. So we put subscript G. When we combine the two, we form, and I haven't talked about this yet, but the ionic compound sodium chloride. All ionic compounds are found as solids at room temperature. They're called salts. So ionic compounds are salts. and they're typically made of metals and non-metals. Those are your salts. So on a periodic table, if I look to the staircase, a metal's on the left, the non-metals are on the upper right. If I have one of each of those, that's an ionic compound. We call that a salt, and at room temperature, it'll be a solid. Now, we've also learned about the law of conservation of mass. I can't create or destroy matter. I can only move it around, break bonds, and form new bonds. So I have to balance this. So the reason why I put a coefficient of 2 here is I have 2 chlorine. So I need to have 2 chlorine here, but I can't change the formula of sodium chloride in the ratio that the chloride is found to the sodium. So I use a coefficient of 2 to show that, okay, on this side, I also have 2 chlorine atoms. But when I do that, I've added 2 sodium atoms. So to compensate for that, I put a coefficient of 2 in front of the sodium. That's the law of conservation of mass, which we discussed in chapter 3. So that's a review of that topic, but it's also a preview of what we'll be doing next chapter, chapter 7, when we're discussing reactions and balancing chemical equations. But let's go to chapter 6 and basically chemical formulas. So one of the things we need to understand is the law of constant composition. That means if I take a compound, it will always have the same ratios or proportions by mass. So let's look at water, okay? If I have 18 grams of water and I decompose it, 16 grams of it will give me elemental oxygen, which is actually a diatomic O2, and 2 grams of hydrogen, another diatomic of H2. But the mass ratios, if I decompose the H2O into its elements, would give me a 16:2 ratio, which simplifies. If I have a 16:2 ratio, if I divide both of these by 2, I would get the 8:1 mass ratio. 8 grams of oxygen per 1 gram of hydrogen. And any sample of water will produce this if it's a pure substance. Realize that tap water is typically not a pure substance. It'll have salts in it, so it will be considered a homogeneous mixture. You would have to have deionized, or what's referred to as distilled water, to get this perfect ratio. But essentially, that's the mass ratio. So we want to be able to represent things in the correct ratios so that we could have the correct chemical formulas. So that's what a chemical formula does for us. The most common way to do this is through what's referred to as a molecular formula. So there's 3 types of chemical formulas. There's the molecular formula. The molecular formula actually tells me the number of atoms and found in this compound, in this molecule. So in this example, I have hydrogen peroxide. Hydrogen peroxide's formula is H2O2. What that tells me is there's 2 hydrogen atoms and there's 2 oxygen atoms in this molecule. There's something that's referred to as the empirical formula. The empirical formula is, you can think of it as the simplified formula. If I look at hydrogen peroxide, the ratio is 2:2. I could actually simplify it and write HO, okay? So that would be the simplified ratio. That's the empirical ratio. For molecular compounds, we'll talk about what those are. Covalent compounds, we do not do that, okay? Where we do provide the simplest ratio are the ionic compounds. So again, I will get into when are we looking at an ionic compound, typically a metal and a non-metal. When are we looking at covalent or molecular compounds? Non-metal, non-metal. But for the most part, molecular compound is how the molecule is found. Empirical formula is the simplest formula. And then there's also the structural formula. The structural formula uses lines to show the bonds. Now, we're calling them covalent bonds. There are different types of bonds, but covalent bonds are the ones found in molecules. It's where the electrons are being shared between the atoms. So here's an example of the structural formula of hydrogen peroxide. Now, this is actually minus what are called the lone pairs. So this is not including the lone pairs. We did this in chapter 4 when we talked about valence electrons and using the Lewis dot series. If you guys remember, hydrogen had one dot, and it had one dot because it was in group 1A and had one valence electron. Oxygen has 6 dots, and it has 6 dots because it's on the periodic table group 6A. So what this is showing is, here's hydrogen's one dot, here's a dot for this oxygen, here's a dot. What it's not showing is it also has the 2 lone pairs. So here's a dot for this oxygen, here's a dot, and then the 2 lone pairs. So the odd electrons, because it wants to pair up, pairs up with the odd hydrogen electron. And that's what this bond is. This bond is basically one hydrogen attaching here and another hydrogen attaching here, so that we have paired electrons, which are essentially bonds. So where do we see examples of, and actually the Lewis dot structure, we'll be doing this later on. This is towards the end of this chapter. First, our focus is, can I just get the formula? I'll draw the structure once I can get the correct formula. So how will I know, when there's an example of a molecular formula versus an empirical formula, which is the simplest? So benzene, okay, it has many uses. It's a lubricant, it synthesizes other organics, but its molecular formula is C6H6, and that's the structure. Now, don't worry about drawing the structure yet, but that is the structural formula, the Lewis dot structure. Acetylene, which is another organic, has the formula C2H2, the molecular formula. What both of these have in common is they have the simplest empirical formula. So what do I mean by that? C6H6. So I have 6 carbon atoms and 6 hydrogens. That's the molecule. But if I was to simplify it, the empirical formula, I would just divide this by 6, divide that by 6. It would be a 1-to-1 ratio. So it would be just CH for my empirical formula. It's the same thing. This is my molecular formula. In the molecule of acetylene, there's 2 carbons to 2 hydrogens. But if I were to divide this by 2, the simplest ratio is CH. So the empirical formula gives us the simplest ratio, but we need to be careful because that doesn't always tell us how the molecule is found. That's why I typically say you want to look at the molecular formula. Once you have the correct molecular formula, like let's do methane, CH4, eventually we'll be able to draw what's called the Lewis dot structure. That's what I talked about earlier. If you remember, carbon had 4 valence electrons because it's in group 4A. These are all unpaired. It wants to have a total of 8, so 4 pairs. So 4 hydrogens come, and then forms 4 bonds. And that's the structural formula. So we'll be learning this at the end of the chapter. We'll also learn how can we look at a simple structural line formula, Lewis dot structure, and think in terms of 3D, because these molecules are not on a flat surface, right? It's not just X and Y axis. That's the big difference from, let's say, algebra and calculus. In calculus, we start to realize, hey, 3D, 3 axes, right? You have, the Y, the X, and it front and back, the Z. Those are polar coordinates versus just X and Y, 2D Cartesian coordinates. So a lot of times you'll see these molecular models. Now, if you can, and I don't want to burden you with money, but if you can buy a molecular model kit, they're extremely helpful because what the molecular model kits is, they allow you to take a carbon, which is the black ball, where typically carbons are denoted by black. They have 4 holes. So the reason why they have 4 holes is they're going to form 4 bonds. That's what carbon likes to do. That's typically why carbon is a central atom, because it could have 4 bonds. So if you look at your carbohydrates, right, your nucleic acids, your proteins, your lipids, what do you always typically find as part of the backbone? Carbon, right? That's why carbon is such a great little atom. Well, now when I attach the white hydrogens, I see that this flat drawing is kind of a misrepresentation to the 3D model. So this is also what we'll be discussing at the end of this chapter, okay? So we have a couple lectures to cover this chapter, at least 4. But today I'm gonna focus just on simple formulas. This is a preview of what's to come. So a particle that's composed of 2 or more nonmetals is basically a molecule. So the chemical formula can express this. So here's an example. We have H2SO4. All right, so this is sulfuric acid. So it's pretty obvious. The subscript 2 means there's 2 hydrogens, the 2 white balls in this 3D model. We have the 1 sulfur. Notice there's no 1 as a subscript. If you write an elemental symbol and there's only 1 of that atom, you don't need to write a 1. It's already inferred because you wrote the elemental symbol. But that's what this yellow ball is. It's the sulfur. And then we have the 4 oxygen, and those are the 4 reds. So here's a 3D rendition of this molecular formula for sulfuric acid. So again, if there's only 1 atom, there's no need to use a 1. So let's practice, okay? So a molecule of the vitamin niacin has 6 carbon atoms, 6 hydrogen atoms, 2 nitrogen atoms, and 1 oxygen atom. Can we write out the chemical formula? And I'm only gonna expect you to do the chemical formula for this, you know, because we're not drawing Lewis dot structures in this particular lecture. But if you were to do it, you know, I have carbon, I have hydrogen, I have nitrogen, and I have oxygen. But what am I forgetting? I have to take into account the ratios. And how do I express those ratios? I express them as subscripts. So the 6 carbon, I see a subscript of 6, the 6 hydrogen, the 2 nitrogen, but for the 1 oxygen, notice I did not do that. In fact, if you do that on your homework assignments and any online, they'll probably mark you wrong because it's unnecessary to write the 1. So don't write the 1. It's, if you write the elemental symbol, that's enough. Sometimes, and you'll see this, we'll have to use parentheses to kind of emphasize the structure. So one example is antifreeze or ethylene glycol. It basically has 2 alcohol groups. An alcohol group is an OH unit. So what they do to show that these are actually 2 alcohol groups is they put the 2 alcohol groups in an OH and then they use the subscript 2. So what does that look like? Well, here's ethylene glycol. So what do we notice? There's 2 carbons. Where are the 2 carbons? Carbon 1, carbon 2. Now notice the carbon is the backbone. Why? Because it could have 4 bonds, right? Because it has 4 valence electrons and it wants to be like neon, so it needs 4 more, so it forms 4 bonds. Then we see that we have 4 individual hydrogen atoms not grouped with anything. So here are my 4 hydrogen atoms. And then the 2 alcohols, and then we put the 2 alcohol groups right there. So how many total atoms are there in ethylene? Well, 2, this is where it gets a little tricky, right? 2 plus 4 would be 6, But if people aren't careful, they might say +2 is 8, but what they're not realizing is the parentheses means there's 2 OHs, not just 2 hydrogens. So the 2 OHs, right? So that's actually 4 atoms. So I have 1, 2 carbons, 1, 2, 3, 4 hydrogens, that's 6 atoms, plus 1, 2 OHs, another 4, that's a total of 10 atoms. So make sure when you have parentheses, you're counting, you're taking the subscript. It's like distributing, right? When I see this OH2, that actually equals 2 oxygens and 2 hydrogens because there's 2 of that group. So when I look at chemical formulas, how do I know what to start with? Like, what elemental symbol do I write? You typically write the most metallic. So if you remember from chapter 4, the metals are on the left side. So if we look, right, here's that little staircase that I always told you that shows you all these are the metals, okay? Whoops, oh, I didn't mean to do that. Let me shrink that down. I don't want to see myself. There you go. That's better. All these are in the upper right corner, non-metals. Hydrogen's over here. It's a non-metal. Some periodic tables put it right there. The reason it's here, it's because it has 1 valence electron. And if you remember, that's why it's in group 1. But we've already seen this. When we just looked at the reaction of sodium with chlorine to produce sodium chloride, we wrote it as NaCl. We didn't write it as ClNa. Well, why is that? Well, sodium is a metal. Chlorine is a non-metal. So I write the most metallic first, sodium, and then the chlorine. Some compounds aren't going to include metals, okay? But in that case, you're going to use the more metallic-like element. So if you remember, we talked about metallic character in chapter 4 as one of the periodic trends. Basically, the further on the bottom and the further to the left, that's the most metallic, right? So as you go down a column or a group, or to the right of a period, makes it more metallic. So we would write nitrogen dioxide or nitrogen oxide and not the other way around. Well, why is that? It's hard to see, but both nitrogen and oxygen are both non-metals. However, what do I notice? The nitrogen's more metallic because it's further to the right than the oxygen. So I write it first. What if they're in the same column? Well, then I use as I go down, a more metallic. So if I look at this, right, do I put sulfur or oxygen first? Well, sulfur, even though it's in the same family, it's going further down. So I write sulfur before I write oxygen. So we're still, when we talk about matter, right, because there's a lot of matter we need to discuss, and the majority of it are mixtures, okay? But we save the more challenging stuff for later, okay, when we get to solution chemistry. Right now, our focus is on pure substances when we talk about matter. And, you know, it's either going to be one type of atom or one type of molecule. We first talked about elements. We focused on elemental symbols, atomic structure, atomic mass, atomic number, how we identify the elements. And right now, today, we're going to look at compounds. So with elements, we could have atomic elements. That's where the element, if we break it down to its individual repeating parts, is just an atom. So like neon gas is just a bunch of neon atoms, okay? The atom is plural or singular for the plural element. But there were those, they call them molecular. I don't like to use that because then people get confused here. I called it the diatomics. Those were the elements where you find them grouped in a group of two, but it's the same type of atom. So oxygen is a diatomic, but it's only one type of atom, so it's still an element, right? Just like the chlorine that we had earlier, it's an element. Even though there's two atoms, it's only one type, so it's still considered an element. When is it a compound? When there's more than one type of atom. Now, there's two types of compounds. There's molecular, sometimes referred to as covalent, and there's ionic, okay? Molecular are true molecules, and they're typically non-metal with non-metal. So hydrogen and oxygen are both non-metals. So this is non-metal with a non-metal. Ionic compounds, they're not really formulas. They're like these complex lattice structures that repeat in their patterns forever. But what the formula tells us is the simplest ratio. It's the empirical formula. And that formula for sodium chloride is a 1-to-1 between the sodium and the chloride. Ionic compounds, not only are they not molecular, they're not non-metal. They are metals with non-metals. So that's how you can distinguish them. That's the power when you have the periodic table and you look at that staircase. That's the power of the periodic table that you use as a cheat sheet. I got metals over here. I got non-metals over here. I should be able, with the exception of hydrogen, it could go over there. But I could look at any formula and right off the bat, if it's a compound, I can determine whether it's covalent or ionic just by looking at the periodic table. But let's further discuss atomic elements. Again, individual atoms. Molecular elements. I like to refer to them as diatomics. The molecular gets people confused because of compounds, all right? But the diatomics, the di stands for two. Chlorine was an example, but you may have remembered from chapter 4, I said, hey, there's 7 diatomics, you need to know them. So you can use the acronym Sir Brinkelhoff, okay? Or you could look at your periodic table and be like, hey, there's a 7 right here, right? Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. But if I actually count the number of elements in the 7, there's only 1, 2, 3, 4, 5, 6. That's because the 7th is the hydrogen. Okay. So you can remember Sir Brinkelhoff or draw the 7 and add the hydrogen. But you do need to know that those are diatomics, even though they're elements. Okay, so that means they travel in groups of 2, but they're one type of atom. There's also other cases. For this course, I don't really emphasize this too much. This is as we move further, but like phosphorus, it's found as P4, or sulfur is found as S8. In this case, this is sulfur S8. Selenium, it's also found in 8. It's because of the structure and how it binds. Honestly, for this course, don't worry about it too much. I just need you to know the 7 diatomics, because when we get to our chemical reactions, you'll see we'll be using those quite a bit. So let's go to compounds, right? Let's focus now. We talked about, in chapter 4, atoms. We talked about the diatomics. Now let's focus on compounds, because that's what chapter 6 is about. And we're going to focus on ionic compounds first. So with ionic compounds, there's typically 1 or more cations. The cations you're going to see have positive charges, and those are typically your metals. And then it's going to have 1 or more anions. Those are the negatively charged particles, and those are my non-metals. Okay. So typically you have 1 metal, as we can see here. All right. So sodium's a metal, aluminum's a metal, potassium's a metal. And then, you you have your nonmetals. So all of these have a metal and a nonmetal, a metal and a nonmetal, a metal and nonmetals. And you can use your periodic table to help you see that. Molecular compounds are just two or more nonmetals. So CO2, right? They're on this side of the periodic table, CH4. Now, why do metals and nonmetals combine, or why do nonmetals and nonmetals combine? The whole goal is to reach what's called an octet. If you remember from chapter 4, when we were doing electron arrangements, all of the elements are trying to be like noble gases. You can think of that. So when we look at the noble gas electron configuration, they have the S sublevel and the P sublevel filled. You can think of it as that S block, which has 2 electrons, and the P block on your periodic table has 6. 2 plus 6 is a total of 8. So metals typically have very few valence electrons. If I looked at a periodic table, right, and I see group 1A, right? If I was to pick, let's say, sodium, let's do lithium. Let's do lithium. Lithium has an atomic number of 3, which means it has 3 protons. But if it's neutral, it has 3 electrons as well. The first 2 electrons go into that 1s2 orbital. The next electron, this is why it's in period 2, it's in the S block, and it's in group 1A, goes in the 2s1. So now lithium, and I could even draw it like lithium, and I can kind of cheat and put 2 in the first energy level and 1 in the second, right? So lithium's like, hey, I want to be like a noble gas. So we could try to gain 7 more electrons and be like neon. Or it could say, hey, you know what? I'm going to just lose this 1 electron. And if I lose this 1 electron, I'm a 1s2 and I'm like helium. So that's what lithium does. It says, you know what? I'm going to lose my 1 valence electron and give it to this non-metal. So if you get a non-metal like chlorine, okay, if we look at chlorine, if I was to do the shorthand ionic configuration, remember I use first the most recent noble gas, it would be neon. And then it would be a 3s2, 3p, 1, 2, 3, 4, 5, 3p5. So it's in group 7A. Why is chlorine in 7A? Because it has 7 valence electrons. So what do we have? 7 dots. 1, 2, 3, 4, 5, 6, 7. However, chlorine wants to be a noble gas. So chlorine wants to be like argon. Now, it could be like neon, but I'd have to lose 7 electrons. Wouldn't it be easier for me to gain 1 and be like argon? Because if I gain that 1, it's a 3s2 and a 3p6 now, and now I'm like an argon electron configuration. So you can kind of think of this as, you know, the chlorine, right? It has 2 in the first shell, then 8 in the second, right? And then it has 7 in the third. Now, where am I getting these numbers? It has an atomic number of 17 protons, so it has 17 electrons. The first 2 go in the first shell. How come? 1, 2. The next 8 go in the second shell. Why? 2s2, 2p6. And the next 7 are right here. So it's going to want to gain 1 rather than lose 7. And if it's by lithium, right? The chlorine's more than happy to accept that electron. And what ends up happening is the metal loses one electron. So if the metal loses one electron, right? So here's lithium. It's got 3 protons. It gives up one, and now it only has 2 electrons. It's going to have a positive charge. That's why metals form cations in positive charges. The chlorine, right? It has 17 protons. How do I get that? Right there, the atomic number. And if it just gained an electron, it has 18 electrons, right? So you can think of it, how do I get this negative charge? Well, what's 17 positive plus a negative 18? Because electrons are negative, -1. So nonmetals, when they gain electrons, they become more negative and carry a negative charge, and they are anions. So they're happy. Now, that's an ionic compound. And what do we notice? An ionic compound is a metal and a non-metal. How do I figure that out? I have a periodic table. I have a staircase. The staircase separates my metals and my non-metals. Okay. Well, when will I share? Is there a possibility for me to share electrons? Yeah, there's a case right here. I could have, let's say, 2 non-metals. I could have chlorine. Why am I putting 7 dots? It's in group 7A, 7 dots. Why? Because chlorine, again, 7A, 7 valence electrons. And I could have bromine that has 7 electrons. Okay, but they want to have 8. So they both need 1 more. So they're willing to share their odd electrons, and then that makes the bond. So that space that the electrons the space where the electrons occupy, if they approach close enough, there'll be an overlap where they can share those 2 electrons. And that's typically how we draw the shared electrons in the overlap of their orbitals. We draw a line. So now I know this is a covalent bond because it's 2 nonmetals, chlorine and bromine. And I know that because they're on the left side of this staircase on the periodic table. So the whole goal for all of these elements is they want to be stable. I mean, really, I hate to personify it, but you can think of it just like people, right? And what makes them stable? Well, having an octet. Why do they want to be an octet? Because noble gases who have octets have their S and P sublevels filled. So that is their goal. So they are willing to lose electrons. So when a metal's around a non-metal, the metal will lose and the non-metal will gain. If there's no metals around, now the non-metals are kind of saying, hey, I still don't have an octet, but I know you don't want to lose yours because you're not a metal and you don't have a few valence electrons. You have a lot, but I'm willing to share with you. So then you have non-metals and non-metals that share because they have too many to lose. So, and no one wants to lose, so no one's really gaining. So they're just willing to compromise and share. This all boils down to the electron arrangement of the atoms. That's why the electrons are so important. And this goes back to, the stability of the noble gases, okay? Now, helium is an exception to the octet rule because it's in period 1, which that energy level, the first energy level, only has the 1 sublevel S with 1 orbital, and it can only fit 2 electrons. When I go further out to the second energy level, now I have the S and the P, so I could add more electrons. So neon, right, it has 8 valence electrons. If I go to argon, it has a 3s2, 3p6, 8. If I go to krypton, now remember, when I get to the 4th energy level, now that valley, the transition metals are there, I fill up the D10, and then I keep going all the way through the P block to the 4p6, but I still have an S2P6, and that's where that octet rule comes from for the noble gases. So covalent and ionic bonds, why? Why do elements form bonds? They want octets. It helps them become more stable, having that S and P sublevel filled. So by losing, gaining, or sharing electrons, they can accomplish this. So again, if there are charges, how do I get charges? If there's actually a loss or a gain of electrons, I call ionic bonds, right? So an electron transfer. So ionic bonds, there is an exchange. Someone loses, someone gains. There's a complete electron transfer, okay? So as a result, you get charged particles. With sharing, no one's giving up an electron, no one's taking it. They're just getting close enough where the electrons are overlapping in the same space, so that's sharing. And that's why there's no charge with covalent compounds. So what's an example of a covalent compound? CO2, right? How do I know this is covalent or molecular? Well, there's two nonmetals. How do I know these are nonmetals? The periodic table. So if I look on the periodic table, it'll tell me. Now, this is missing the lone pairs. We'll get into that a little bit later. The reason why is when you look online, typically the structural formulas omit lone pairs. We will not omit lone pairs in our drawings for this course, because to get to the level where you can omit it, you got to understand that they're there for the octet first. Yeah, that would be an example of the ball and stick model. Ionic compounds are, again, metals and nonmetals, and they form positive charges. Because they're not actually a molecule, so when I look at CO2, I have a molecule with the 1 carbon and the 2 oxygen, and that's pretty much it. I can shrink it to an individual molecule. With ionic compounds, there's basically this repeating structure that goes on, but the formula is derived to make the compound neutral, okay? So why is sodium chloride neutral? Well, okay, sodium is in group 1A. What does it do? It loses 1 electron. That's why it forms a positive charge. Chlorine's in group 7A. So to get an octet, if it has 7 and it wants 8, it needs 1 more. 1 more negative makes it a negative charge. So what I notice is if I have a positive charge and I add a negative, it equals 0. It's neutral. So how can I predict charges, right? Well, like how would I know that potassium, right, is going to form a positive charge, a positive cation? Well, okay, let's look where potassium is. Energy level 1, 2, 3, 4. So if we think about it, right, potassium, if I have it as an atom, the first 2 electrons go into the second energy level. The next 8 go into the second. I think I said the first 2 go in the second. I meant first, I'm sorry. The next 8 go into the second energy level. Then we have 8 more going into the third. And then in the last shell, the 4th period, it has 1 valence electron. Okay. So that's why it's in group 1A. So it has a choice. I could try to gain all these electrons, okay, to be like krypton, or I could lose 1 and be like argon. And what does it do? It loses the 1. So for the most part, group 1A, right, it has 1 valence electron. So is it going to try to get 7 or lose 1? Lose 1. That's why they have positive charge. Group 2A have 2 valence electrons. So what does it want to do? Does it want to try to get 6 or lose 2? It's easier to lose 2, so it has a 2+ charge. Group 3A, what does it want to do? Well, it could try to gain 5 more, right? So 1, 2, 3, 4, 5 more to be like a noble gas, group 8A, or it could lose 3. Now, when we get to 4, you notice like carbon, and carbon, it can form a 4 plus or a 4 minus, and that does occur. But for the most part, carbon is never, for the most part, it's not in ionic compounds. It's in molecular compounds where it shares. Why? It's in the middle, right? So it doesn't really want to lose or gain. It'd rather share. Okay. So 1 through 3A, they have few valence electrons they like to lose. Once we get to 5A, okay, so sodium has 5 valence electrons. How do I know that? 5A. What are the 5 valence electrons? Well, if I wrote the electron configuration for nitrogen, it would be 1s2, because the first 2 electrons go in the first energy level and the s sublevel, and then you would go 2s2, 2p3. Why 2p3? It's in 1, 2, the third position of the p block. So it has a choice. It could lose these 5 valence electrons, right? Group 5A, or it can gain 1, 2, 3. What's easier? Gain 3. Gaining 3 negative charges, 3 electrons, gives me a 3 negative. What about oxygen? Lose 6 valence electrons or gain 1, 2? Gain 2. Gaining 2 negative charged particles would give me a 2 negative charge. Same with fluorine. Lose 7 valence electrons or just gain 1? Gain 1. Why? You have all these group 1As that are willing to give it 1. Okay. Now the transition metals, right here, there's a few that are special and they have pretty consistent charges. And those are those in that triangle right there, okay? All the other metals in the transition metal block can have more than one charge, and I'll talk about that in a second. But to remember these, you could draw this triangle. I like drawing a little staircase. Excuse me. So this is the third stair, and aluminum is a 3 plus. Zinc is on the second stair, and silver is on the first stair. So I have an increase in charge, +1, +2, +3. I actually emphasize this in some of my videos with electron configurations of transition metals and their irregular patterns. So this would be an example of irregular electron configurations. For this course, I'm not going into it. I'm just letting you know that silver is +1, zinc is +2. Okay, you have to pretty much know that. And you can use that triangle or the staircase. Okay. How do I predict the anions? Again, chlorine, it's group 7A. So is it going to lose 7 valence electrons or gain 1? It's going to gain 1. If it gains a negative charge, it becomes negative. So I kind of already covered that. Okay. So the non-metals form anions, which are negatively charged, and the metals, because they have fewer valence electrons, form cations, which are positively charged. I always remembered metals form cations, which are positively charged, because they're losing a negative thing. So if you lose something negative, that's positive. Anions are negative because they're gaining electrons, which are negative. So why is that important? Well, now that I understand how to predict charges for metals and non-metals, now I can determine ionic compounds and their formulas. So we're going to start with the easiest of all probably ionic compounds, which is binary ionic type 1. So what does that mean? You basically take the name of the metal, you write it out in full, you take the non-metal's name and you cut off its ending and add the "ide" suffix. So a lot of you already do this. So it's not sodium chlorine, right? Because chlorine is the elemental name. Because it's in a compound, how do I know this is a compound? Well, there's more than one type of atom. So because chlorine's in a compound, and it's the second element, because it's the nonmetal, I cut off the end and add an "-ide" suffix. And I see that with all the nonmetals with binary ionic. Why is it binary? Well, what's a binary language? O's and ones. There's two numbers. Binary means two. Binary ionic. Well, how is it ionic? That's because I have to have a positive charge and a negative charge. That's why it's ionic. Well, to be binary ionic, that means I have one metal and one non-metal. Sodium's the one metal, chlorine's the one non-metal. Sodium chloride. Magnesium's the one metal, bromine's the one non-metal. Magnesium, I cut off bromide. The two just tells me the ratio based on charges. There's two bromides per magnesium, but there's only one type of non-metal anion. There's not multiple. So potassium and sulfur, potassium sulfide. There's one of each, one metal, one non-metal, so it's binary. Binary ionic. Why is it ionic? Metal, non-metal. So how do we get a formula from the name? So typically if we see the formula, it's a lot easier. You know, when I look at this, I mean, I'm pretty comfortable you guys are solid. Like if I wrote this, how do I know that that is ionic? Calcium is a metal. I just look at the periodic table. Oxygen is a non-metal. Why did I list calcium first? I list the metal first. I write the full name of the metal. Calcium. For the non-metal, I take the root, cut off the end, and I slap on the "-ide" suffix. Calcium oxide. Okay? So it's a lot easier when you see it to name it. So, for example, if I wrote this, you would look at it and be like, all right, lithium's over here, it's a metal. So that's why I wrote it first. And fluorine's over here, and it's a non-metal, so I'm going to cut the ending and add "-ide." It's fluoride. And I know it looks goofy, but this is actually the correct way to spell it, even though usually you would think OU, but with fluorine, it's UO. What's harder is going from the name to the formula. When I see the formula, I can name it. It's a lot harder doing the opposite. So what you have to do is you have to look at the periodic table once you see the name, find the elements, what group they're in to determine their charge. Okay, so aluminum's a 3+, oxygen is a 2-. Why am I putting charges? Well, it's ionic. Well, how do I know it's ionic? It's a metal and a non-metal. How do I know that? Periodic table. I look at the periodic table and what do I notice? Aluminum's a metal. Why? It's on this side of the staircase. Oxygen's a non-metal. Why? It's on this side of the staircase. Aluminum is a 3+. Why? It's group 3A. It's easier to lose 3 valence electrons than to gain 5. Oxygen, it's a 2-. Why? Group 6A. It's easier to gain 2 electrons than lose 6. Okay, now I've identified the charges by using the periodic table. How do I get the formula? I got to make sure this is neutral. The easiest way to do this, I call it crisscross. Take the charges of each ion and use it as a subscript for the other element. Crisscross. Now, it can get tricky. I get it. So let's do sample exercise 1 and get some practice. So we need a periodic table. Now, your periodic table might not have the charges. That's okay, because you're going to be able to determine the charges because you got your group numbers. Those are going to help you. Okay, so when I read this, sodium nitride, what does that mean? There's sodium and nitrogen. So I have to find those. Here's sodium. Okay, it's in group 1A. That's why it's +1. So I might write sodium +1. Then nitrogen. Oh, it's group 5A. Am I going to lose 5 or am I going to gain 1, 2, 3 to be like group 8A and have my octet? I'm going to gain 3. Who's going to give me 3? Well, the sodium, of course. Well, I can't have a 1-to-1 ratio because it needs to be neutral. So what do? Crisscross. When I do that, I see that I need 3 sodiums per 1 nitride. Why? I need 3 + 1 charges, right? I need 3 + 1 to cancel out the -3 and give me a neutral charge. So next, calcium chloride. Well, look at the periodic table. Here's my calcium. Here's my chloride. Calcium's group 2, 2+. It's a metal. Chlorine, non-metal. This has got to be ionic. I got a metal and a non-metal. Calcium 2+, group 2. Chloride -1, 7A, because I need 1. So I would go calcium 2+, chloride -1. What am I going to do? Crisscross. Oh, I already did it. It's right there. But yeah, so this is a mix. That would show you how to get, if I gave you the name, the calcium chloride. Sorry, I got a little goofy right there. We'll do a potassium fluoride or sulfide. So let's do potassium sulfide. I'll clean it up here. Pretend we're starting from scratch. So I got my periodic table. Potassium. It's not P. Oh, that's funny. They don't have phosphorus right here. It's not P, that's phosphorus. It's K, Catrium. So here's my potassium. It's K+. Why? Group 1A metal. Sulfide, it's a 2-. Why? It's a group 6A non-metal, 1, 2. So I need how many potassium to sulfides to make this neutral? Well, you can just crisscross. K2S. Now I see Mg, magnesium, and I see O, oxygen. Is this ionic? Yeah, magnesium's here, oxygen. I got a metal and a non-metal, so it's magnesium, cut off the end, oxide. Now someone might say, well, wait a second. Why is it a 1-to-1 ratio? Magnesium is 2+ and oxygen's 2-. If I crisscross, like you've been telling me, it would be Mg2O2. This is not a molecule. There's not these shared bonds. This is a repeating pattern, right, in a lattice structure. So for ionic compounds, it's not a molecular formula. It's really called a formula unit, and it's really the simplest ratio, the empirical formula. So we're dividing this by 2. That's how we get that 1-to-1 ratio. I only need 1 magnesium to neutralize the 1 oxide. So it's a 1-to-1 ratio. Now, I wish we were done with ionic compounds, but there are some metals that form more than one type of charge, okay? So when I was looking at the previous slide, notice I'm looking at what is referred to as the representative elements, right? And I was telling you, well, you should know that zinc is 2+, cadmium's 2+, and that silver is +1. But in the valley of transition metals, I can have more than one type of charge. Why? The transition metals have this D block. So it's really hard for them to lose 10 electrons sometimes and to get a filled S&P. So what they try to do is they try to get their sublevels all the way filled, halfway filled, or all the way empty. And I actually put an extra video for lecture for those additional, more challenging orbital diagrams for this course. But for the most part, you got to know that transition metals can possibly have more than one charge. So what do? Well, First, I got to realize, where are they located? In the valley. So here's an example. Iron. They can form a 2+ charge or a 3+. So it could have multiple charges. So if I wanted to combine with chloride, and remember, chloride has a -1 because it's group 7A. It's only one charge for chloride because it's a representative element. What do I mean by representative element? They're in the S and the P block of the periodic table. But if I just say iron chloride, I won't know the correct formula because I don't know if it's the one with the 2+ or the 3+ charge. So that's ambiguous. So what do I need to do? Okay, now we're still binary ionic. What do I mean by binary? 2 elements. Ionic. Well, the 2 elements are what? Metals and nonmetals. But these metals are transition metals. So I'm calling this type 2 because I can have more than one charge. So how do I show that? Typically, I take the transition metal's name and I add a Roman numeral to tell me what the charge of that transition metal is, and then I write the nonmetal. So what's an example? Iron 2 chloride, iron 3 chloride. Now, back in the old days, we had to memorize all the charges. And we not only did, this is referred to as the stock system. Stock system is superior in the sense that the Roman numeral tells me the charge. We also had to know the old Latin system where we didn't use Roman numerals. We used the ik and us suffixes, and we also had to know the Latin name of these elements. So you would have to know that iron was ferrum, and you would have to determine whether it was ferrous chloride or ferric chloride. The way you do that is you would look at the charges. Now, someone might say, well, how am I going to remember that iron's 2+ and 3+? Well, if I look at chlorine, the one thing I know about chloride, I know it's a -1, right? So if there's 2 of these, that's got to be a -2 charge. So what's going to cancel out a -2 charge? A +2. Well, there's one iron. It has to carry a +2 charge to cancel this. So this has got to be iron 2 chloride. It'd be the same thing with iron 3, right? If there's 3 chlorides, right, I got to cancel out that -3. So how do I do that? I got to have a +3. And typically you actually, what I'm doing is actually conventionally not correct. You should have the charge after the number. So I'm getting a little lazy, but you're supposed to write it for conventional purposes, the charge after. But I need a 3+. So if I have one iron and it has to carry a 3+ charge, it's got to be iron 3 chloride. So that's how we use the Roman numeral stock system. Now, for this course, I don't expect students to do the old system. I like to go over it because we had to, we actually had to know it all. But I like to go over it because if you look at the back of an IV bag, it'll say ferric chloride. If you look at, any household products, they use the old Latin system. So it's good for us to know. So the first thing we need to know is the Latin word for iron is ferrum. And we have 2 prefixes, the ik and the us. So how I remembered it when I was school is the us sounds like the lesser charge. The ik is the higher charge. So iron 2 is less than iron 3. So this would be ferrous chloride. And this would be ferric chloride because it's the 3, right? So this is a lot harder because you don't have the Roman numerals telling you the charge. So you'll have to memorize the charges. So if I see like ferric chloride, I'd have to memorize that iron is either +2 or +3. But if I saw iron 3 chloride, I don't have to memorize anything. I know the charge is 3. So the old system is definitely more challenging. So for fun, okay, we're going to do first the stock system for this, and then we're going to do the old system. Now, I'll help with the old. Copper, Cu. The Latin name is cuprum. That sounds so funny. Remember, you got the ick and the us, and you can use my goofy little thing. The us is less of a charge. Okay, so if I was to have the stock system, I'm just going to say copper and then Roman numeral charge oxide. So I know both of these have oxygen. Let's look at this one. I look on the periodic table and oxygen has a 2- charge because it's group 6A and it's 2 away from the noble gas. So if it's a 1-to-1 ratio with copper, what charge would cancel out 2 negative? It's got to be a 2 positive. So this would be copper 2 oxide. Okay. Same thing here. I got oxygen. It's a 2-. 2+ cancels it out. However, this 2+, there's actually 2 coppers, not just 1. So this 2+ is shared over 2 coppers. So what I do is when I figure out the charge given by the anion, the total charge is a -2. I divide the total positive charge by the number of transition metal. So 2+ divided by 2 means that this must be copper 1 oxide, because each copper has a 1 charge. And you could even go back and do this and be like, oh, whoops, sorry about that. I went straight up to diatomic. You could use a crisscross, right? If this was +1 and this is 2-, oh, that makes sense. So this is copper 1 oxide. Now that you know the charges, because you can use the non-metal to determine the charges, but I see both. I see that there's copper 2 and copper 1. I don't have to memorize, right? But it's always 1 or 2 for copper, right? I'm telling you, it's 1 and 2. Now I can say, oh, this must be cupric oxide and cuprous. All righty. So again, if you had iron 3 fluoride, could you easily do this? I think you could, right? You could basically say iron, oh, they're telling me it's 3, fluoride, boom, crisscross, and I'm going to get FeF3. But, you know, to do what I was saying earlier, the 3 Roman numeral means a 3+ charge. Fluoride has a -1. Right? I need to cancel out a 3+ charge. How do I do that? If I have a -1, I need to multiply that by 3 so that this becomes a 3 negative to get a neutral charge of 0. Or you can do what I was saying from the very beginning, crisscross applesauce makes your life easier. I'm kind of hungry right now, but anyways. All right, determining ionic charges. So how do I do that? This is what I was talking about earlier with the copper. What if I'm given, you know, the formula, right? Because it's always easier, you know, if they tell me the charge, right? If they're telling me it's a copper 3, I already know it's copper 3. What if they don't? What if they give me the formula and I see this? Now, first, how do I know that this can have multiple charges? Because if it doesn't have multiple charges, then I don't need to use the Roman numeral stock system. Well, the reason why I know it has multiple charges is chromium is in the valley. It's in the D block. It's not in the representative elements of the S and the P block. So right off the bat, as soon as in the valley, the transition metals, I got to say, boom, this has more than 1 charge. I need to remember Roman numerals for this charge. Okay, now how do I determine the charge for chromium? Okay. Each nitride is a 3 minus. There's 2 of them. So that gives me a 6 negative. Okay. So I have a total negative charge of 6 negative. Each nitride's 3 minus. There's 2 of them in this formula. So that means that the chromium, all of them, have to give me a 6 plus charge to make this a neutral ionic compound. Because 6 positive, 6 negative equals a net charge of 0. Because atoms and compounds are neutral. Ions are not. These ions are not. But when the ions come together to make a binary ionic compound, the compound's neutral. Okay? So now I know that all the chromiums give me a 6 plus. So what does the chromium have to be? Well, there's 3 of them, right? There's 3. It says right here. So chromium X plus, X plus, X plus equals 6 plus. So each must be a 2 plus. Another way of doing it is just take that 6 plus and divide it by this subscript 3. So that must mean it's chromium 2. So this would be called chromium 2 nitride. How did I do that? Did I memorize that chromium has a 2 plus charge? Nope. I used the non-metal anion. I used its charged. So I used the charge of -3 on the nitrogen. I used the chemical formula subscript to determine the total charge of the negative. And then I knew it had to be electronically neutral as a compound. So I knew if this was a 6 negative, this had to be a 6 positive, because there's 3 of the chromium. 6 positive divided by 3 gave me the 2 plus charge. All right, let's do it. So let's do a little bit of the binary ionic with transition metals that can have more than one charge, okay? Now, a lot of, like the molybdenum, the tungsten, I tend not to do that to students because those are elements that aren't that. Tungsten's actually pretty important. I mean, it was the first filament in light bulbs, but I don't expect students to know those elements. These other elements, yeah, I do, kind of, okay? So how am I going to approach this? Well, Mn, it's not Mg, okay? So first of all, it is not magnesium. Now, if you say magnesium, you got it wrong. When you look on the periodic table, you'll see that Mn is in the valley. So that's always good to have a periodic table when you're doing your work. It's like your little cheat sheet. It's in the valley. It's manganese. But because it's in the valley, I know that it's a transition metal and can have more than one positive charge. So I have to figure out, well, how am I going to figure out what the charge is? Well, my friend, you got oxygen. Oxygen is what? 2 minus. There's 2 of them. Times 2. What's 2 times -2? -4. So I need to cancel out the -4 with what? A +4. There's only one manganese. So this must be manganese 4 oxide. And yes, the Roman numeral 4 is expected of you. All right. Copper 2 chloride. The stock system is nice. It's telling me, I didn't tell you this was cupric chloride. It's copper 2. So what does that mean? The copper has a 2 plus charge. Now I go to the periodic table. I see, oh, chloride has a negative, right? So this must be copper 2 chloride. What did I do? Boom. Crisscross applesauce. So AU, arum or rum for gold, okay? Now, you don't need to use the old system, right? You can just say gold. You look for AU, you see it's in the valley. You're like, he's trying to get me to transition metal, but he can't get me because I know there's more than 2 charges, but I'm good because I know chloride has a -1 and there's 3 of those bad boys. So that's a 3 negative. So I need a 3 positive to cancel out. This must be gold 3 chloride. See? Molybdenum 6, that's a 6, okay? So this would be 5, right? V Roman numeral 5. This is 4. And now with the 1 after that is 6. So this is molybdenum, which is HMO, and it's a 6 plus charge. And then I got fluoride, which is -1, so it's MOFA 6. Yep. I like it a lot. So then last but not least, I try to find W. I need a W. I need a W in this class. I look, it's in the valley, okay? I don't want to remember, the Latin word. I'm just going to use a stock system with Roman numerals. I don't have to memorize tungsten's charges because, I know oxygen is 2 minus and there's 3 of them. So that's a 6 minus. How do I get rid of a 6 minus? I need a 6 plus, but hold up. There's 2 of these tungstens to cancel that 6 plus, right? So when I divide that 6 plus by 2, I get a 3 plus. So this is tungsten 3 oxide. Yup, tungsten 3. Good times. All right. So here is an example of, different transition metals and their Latin-derived names, okay? Again, I don't emphasize, I just don't. But I did go over, cuprum and ferrum, okay? I love this one. It's actually, this is the us and the ick, because this is a lesser charge. 2 is less than 4, so it's plumbus and plumbum. But lead is plumbum. I love plumbum. I remember I thought that was so funny when I was at UCSD because I'm by PB, plumbum. Anyways, so we're going to use the stock system. It's a lot easier. And we're going to fully utilize that crisscross crossover system. That's what I did earlier to show you. Hey, if someone tells me you have aluminum oxide, this happens all the time. Because students, they watch lecture, and they're like, this is easy, man. This is easy. And they're like, aluminum, boom, oxygen, boom, I'm done. No, you're only half right. So if this is worth 2 points, you get 1. Why? You don't have the correct ratios. What this person did not do with the boom is they didn't realize, hey, aluminum's a metal. Oxygen's a non-metal. Oh, snap. This must be an ionic compound. Oh, if it's ionic, that means there's charges. The metals form positive charges, the cations, the non-metals form negative charges and ions. How do I determine the charge? The periodic table. Then once you determine the charges, you do the crisscross, and you don't do boom, you do boom, and you get 100%, not 50. There you go. Oh, there you go. Try that. Does anyone know the name of that? Well, let's first figure out what are we going to do? Are we going to go crisscross? All right, this I know why I did this one. All right, we do this crisscross, boom, boom. Now here's a tricky thing. Oh, I forgot the plumbum. Sorry, let me get that up in PB2S4. Now with ionic compounds, what did I say? We're really looking at the formula unit, which is the simplest. So you would think it's that, but in actuality, I want to simplify. 2 goes in here, 2 goes in here. So it's PBS2. Now, what's the name for PBS2? This is lead 4 sulfide. And this is tricky because if you do a reverse crisscross, someone might think that this is lead 2. So you need to be careful. You need to make sure that you know that, hey, sulfur is 2 minus. And if there's 2 of them, I need to cancel out that -4. So this has to be +4. So just be careful. Don't be, booming up in here. Okay. We're done with the binary ionic. So type 1 binary ionic, easy smeezy. Just look at the representative elements. Boom, boom. You have the charges. It's always the same. Binary ionic with transition metals, type 2 is that's a little bit harder. I'm not going to lie. Why? Because now there's more than one charge and you have to determine the charge based on the non-metal. But I know you can do it. It's going to take a little work. I actually think the binary covalent is easier. Okay. Why? Non-metal with non-metal, no charges. Okay. So this is type 3. It's still binary. Why? I have two different atoms, right? Because it's a compound, right? To be a compound, you have to have more than one type of atom. Binary means there's two, but it's covalent, also sometimes called molecular because it's a non-metal with a non-metal, where we're sharing electrons instead of a complete electron transfer where there's charged particles as a result. Because we're sharing, there's no charges. So how do we do this? The one that's most metallic goes first. So how do I know? Right? The further down or the further to the right, the more metallic. Okay. There is an exception with halogens that are bound to oxygens. You're going to list the halogen first. So group 7A, if you bind fluorine, chlorine, or bromine or iodine with oxygen, even though the oxygen is more metallic, you're going to list the halogen first. That is an exception. I apologize. It's not perfect. Okay. The second element, this is also confusing, also has an "-ide" suffix, even though this is not ionic. So in both ionic and covalent, the first element, you write the full name. The second element, you cut off the end and put an "-ide." The second element is always a non-metal. In covalent, the first is a non-metal, but in ionic, it's a metal. Okay. But now, because we don't have charges to predict ratios, because we got to get the right ratios, the subscripts. Like I need to know if it's CH4 methane or C2H6 ethane. So how do I do that? I'm going to use prefixes. That's funny because those organic compounds, I didn't use them. But for inorganic, we're going to be using the prefixes, okay? So what are the prefixes? Mono, uno, right? One, die, dissect, cut something in half. Two, try, triangle, three sides. I personally think 4 is the hardest, the tetra. We usually think quad, like quadrilateral. There's 4 muscles in your leg. Quadruped, an animal that walks, on 4 legs. But here we use tetra because a tetrahedron is a 4-sided figure. That goes back to this structure right here. It actually has 4 sides. It's a pyramid with a triangular base. There's one lateral face here, one lateral face here, one lateral face here, and one lateral face on the bottom. That's 4 faces, or I said one lateral face on the bottom. One base face, 3 lateral faces makes a total of 4, a tetrahedron. After that, it's pretty easy. If you remember geometry, right? So a pentagon, right? That's structure and, DC. Penta means 5. Hexa, you think of a stop sign. It's a hexagon. Hepta, I'm not going to do that. Heptagon. Octa, octopus, 8 limbs. Nona, 9. Deca, decade, 10. That's all we need. There's more than this. We'll just focus on 10. Okay, so these are the prefixes. So with binary covalent, I know it's covalent because I'm going to use a periodic table. I'm going to see non-metal with non-metal. I don't have charges, so I have to indicate the ratios using prefixes. Okay. So here are some examples. Chlorine, oxygen. Now, I think I skipped over this quickly. I apologize. You always use prefixes, except when there is only one atom of the first element. So what do I mean by that? This is carbon dioxide. Notice there's one carbon. I did not say monocarbon dioxide. I didn't. This is carbon monoxide. So for the second element, you always use prefixes. Always, 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 always. Even if there's one. With the first element, you always use prefixes except if there's one. So now we see that that's not monochlorine dioxide. It's just chlorine dioxide. And even though a halogen is less metallic than oxygen, that rule, we put the halogens as the one exception before the oxygen. Now, the first element, nitrogen. Nitrogen's more metallic than oxygen. We list it first. It's further, to the left, so it's more metallic. There's two nitrogen, so I got to use the di prefix. So it's dinitrogen. Oh, I love this. There's 5 pentoxide. Then I got disulfur dichloride, selenium hexafluoride. Notice with the fluorine or the fluoride, the U before the O, people always spell that wrong. So I think this is typically a little bit easier. Let's figure out the formulas, and from a formula, the name. So A, dichlorine. Okay, I know there's chlorine, and di must be 2. Heptoxide. Okay, 07. Whoop, I forgot Yep, carbon. There's one carbon. I don't need a mono prefix. Okay, tetrachloride. Tetra replaces quad, so it's 4 carbon tetrachloride. Then I see that there's 2 of those nitrogens. I have to show that there's 2, so I have to write di nitrogen. There's 2 fluorides, difluoride. Okay. Now, binary covalent, right? Binary covalent basically means non-metal, non-metal, and I have to use prefixes. There's a special type of covalent or molecular compound. They're acids. And what actually happens is, even though hydrogen's a non-metal, when I throw acids in water, the hydrogen releases in water and forms a cation, the hydrogen ion, which is referred to as proton. That's why later when we discuss solutions and acids and bases, we'll see that we use the definition as a proton donor or proton acceptor, because the hydrogen ion is a proton, because all a hydrogen atom is a proton in the nucleus and an electron. If I remove that electron, all that's left is a proton. But typically how it works is if I throw an acid in water, so here I have hydrogen with 1 valence electron, chlorine with 7. However, as they approach, those odd electrons overlap unfilled orbitals, and that forms a bond, okay? When I throw this in water, chlorine gets mean. Chlorine's like, you know what? I am a non-metal. And I know you are too, hydrogen, but I'm way better at taking non-metals than you. You only got 1 valence electron. I got 7. I want to get 8. I'm gonna take that from you. So what happens is chlorine, when I throw this in water, steals hydrogen's electron, and it forms the chloride ion. So why is it the chloride ion? It stole the electron from hydrogen, and hydrogen forms a proton, or the cation hydrogen ion. So that's what acids do. They're covalent compounds, which means non-metal, non-metal, but one of the non-metals is hydrogen, and when you throw it in water, it acts like an ion, loses its electron, and that's because the water molecules can stabilize the charge and surround that proton. So there's 2 types of acids, and because there's 2 types, there's obviously going to be different namings. There's the binary. So I like the binary. Binary. Binary means two. To what? Well, to be an acid, I have to have hydrogen and then a non-metal like this. So this HCl is an example. It's got hydrogen and a non-metal. The other type is an oxyacid. They have hydrogen, a non-metal, and oxygen. We saw that earlier with the H2SO4. We have the hydrogen, the non-metal is sulfur, and then the oxygen. The name is derived from the non-metal. This is sulfuric acid, but we'll get into that next lecture. Okay. What I want to get into for this lecture is the last binary substance. So far, binary ionic with transition metals, binary covalent, and now we're going to do binary acids. And how do I name this? I know a lot of you already know that this is hydrochloric acid. I know you know that, but now we're going to talk about why. So if it's binary acid, how do you know? Hydrogen and a non-metal. You throw it in water, it's going to be an acid. You're going to put a hydro prefix. You're going to take the base of the non-metal, cut off the ending, add the ic acid suffix. So hydro prefix, chlorine, cut off the ending, add the ic suffix, and then acid. Hydrobromic acid. Hydroselenic. Now, there's more, right? What about that? Hydro. Why am I using the hydro prefix? It's a binary acid. How do I know it's binary acid? There's only hydrogen and a non-metal. Hydro, fluor, because fluorine, ic, acid, suffix. Now, I should have aqueous, because what that means is I'm dissolving in water, and that's why it's behaving as an acid. Okay. Another example. Hydro, iodine, iodic acid. Hydroiodic acid. So we are done for this lecture. I know that was a doozy, but in this lecture, we covered the differences between ionic and covalent compounds. Ionic, metal, non-metal, a complete electron transfer. One loses, one gains. That's why we have charges. Metals are cations, positively charged. Non-metals are anions, negatively charged. Covalent compounds, no complete electron transfer. Why? Covalent compounds, non-metal, they want to share. So we have a sharing. So because there's no charges, we use the prefixes. Those are binary covalent. However, there are binary acids where the non-metal gets greedy and steals the hydrogen's electron when you throw it in water. And those are the binary acids. So next lecture, we'll talk about the oxyacids, and we'll also talk about what's referred to as polyatomic ions that are seen in ionic compounds. So thanks so much for tuning. Thanks for being patient, and I'll see you next time. Bye.